So in this video I will show you around the Save System examples. The framework comes with quite a lot of examples you can take a look at. We have 5-minute save. That's the example we are starting in this series. We have account and slot management. We can take a look at this. The Save System comes with kind of an account system. You can use it to handle different players on one device or different accounts on one device. It's not meant to be a multiplayer feature at this point, but we can take a look how to use the accounts. We have account management. We have account badges, which is 0. We could simply change that by typing in a number, and then we have badge 1 if we would split many accounts, different badges. It's there, you can use it, and we stay on badge 0 and enter a new account, example account, and we are creating an account. That's good. We can select example account here and set the account active. Then in an account you have save states. Save states are basically a save slot. And save state is a complete state of a game moment. So you could have multiple save states for different slots, or you can have multiple save states for like in character management. And you can say I need slot 01, slot 02, and so on, and you can handle it like a premium feature. So with premium currency you get an additional slot. Maybe the slot is bound to the save state of a character or something like that, or simply more slots to save in. And you can set the slot active, and we can write data to the slot to test it. So we have write data. We open the save location, and we see we are in the example accounts in the badge 0, and we have save state, and we have slot 1. We are writing the files in, and this is the test data. We have test objects ID, and we have a temp folder. In the temp folder we are holding our backup for all the save data, because we can simulate a write failure, which means if there is a blackout during save or something like that, if the save operation don't end and breaks in the middle, then there is a meta info file missing, and we know on that's corrupt. So that's simulated by deleting this meta info. So you see the system is knowing that it's corrupt, and it's knowing we have an backup, and we can simply restore it. So that's all there's to it. We can delete the slots, we can handle it, and this example shows you how to do the account part of the game. But please note that's not it's not a multiplayer feature or a server head feature at this moment, at this time. And the next example, runtime handling, that shows you how to handle objects that are in scene objects. The circle, for example, you get your circle, set it in a scene and lives in a scene, and you also are able to spawn the circle during runtime, and the logic to do so differs, and you have to handle it in the code to differentiate it. And we can, you see, spawn this. We can have a rump save, we can rump for file, which means we are only loading the rump state, and we spawn more. We can rump state, the small spawn, the additional gets deleted. We have a file save, we are saving to file. We have also a duration on that, and spawn more, reload from file, additional ones gets deleted, and the life cycle of this hybrid game object is explained in this example. This is kind of necessary if you want to have an open world like an Skyrim type of game, and you want to have your own spawner and can spawn a game object over the spawner or set it in the scene in the editor or whatsoever. So you can take a look here how to do it. Next, we have scene handling. We have scene handling. There is a thing you have to do before you can use this example as explained in the README, because this is working on scene name. We just have to add those scenes into the scene list, so we are able to identify the scenes. And this is done. We can start it. And here you can have a quick look. We have our dude. He can run around. He spawns a little object every 3 seconds, and this little object gets saved after we are changing the scene. You see they're there, and that's a fully I/O operation on scene change. And the red balls are listened to the save events, but not has no place in a file, just reset their state during runtime over the events. We have here a little flag that will let us checkpoint save into RAM, and if we are dying after that, we are just respawn here. And you see the objects are resetted. The next scene shows you the broom. You can collect it, and then you are no longer spawn the game objects, but you are able to clean the objects and done. This cleaning is part of a method to show you how to change the way you access data on different game objects, because the dropped object stopped to participate in the save routine. It's unsubscribed from all methods. You can't, and so on. And the broom are able to, you see it in the makes you able to manipulate that data afterwards. So you can hold the control. Here's this test the migration test. It simply explains how the migration works on an AQN, also on the assembly qualified name. We have so imagine we have the version 1 data saved to file. What's already done on these buttons, then we have to increase the global data, which we do now. And you see, qualify, and we see load migration that did physically migrate the data during the code, and you see migration successfully, data loaded as custom iSave data 2. We can take a quick look. This is version 1. We can't just delete it in this example because we are starting always with this and we need it. But in a normal project, you just would have this reader from the version 1. And you can see how it's done in this. And then I added some async examples, but you do not have to change that much for an async save because the game objects works the same way. Only thing that's change are the save triggers, and you can, for the example, the coin, as the 5 minutes example, will show you on the save button how to use the async triggers to be able to fully asynchronous save to the file system. So yeah, this is all the examples there is. We have the performance. Did we talk about the performance test? No, just started. This is created to test the performance during development also, and to give you a tool in the hand. You can see how the system performs on your device. So for example, I have an old i7 77K, so on newer hardware the times would be way better, and if we would use it in a build setup, not in the editor, you would even get better results. So the example shows you 2 red balls to indicate frame stutter. So you can set the dirty amount of the objects. We can spawn on an element MD, which means each object is an own file, and we can spawn on subkey. Subkey which means the objects are saved in one file, which makes a big difference how fast the I/O part of the saving is. But for the example, we are writing every single file per object. We are spawning some in, and we take a snapshot, and you see we have this much elements, and the single snapshot took that much time. So let's do an average out of 50 iterations. The max spike could be the editor and the garbage collector of the for the editor, and we can use the garbage collector analysis, which shows us the average time on a snapshot, how much data is allocated, and per element how much data is allocated, and then output. So, and we can test full I/O save. You see, took because we have over 1000 files to write, and we take an asynchronous save, and you see it took a little bit longer, but you don't have a frame stutter if you are doing this. So you see, and there you can test the performance and see at what point you would get a frame stutter if you are frequently snapshot the data into RAM. You see, the snapshot is the only real blocking part if you're using asynchronous I/O operations. So that is all to the examples. You can take a look at them and play around so you learn the system even better, and I hope your projects will be integrating the Kobeltstuff Save system.